Hello, everyone. I'm Zhiming. I'm doing postdoc with Dr. Yongming Liu at Arizona State University. Today, I will talk about the knowledge discovery of nonlinear dynamical systems. In this work, we developed a PDE-learning method, a Parsimony-Enhanced sparse Bayesian learning method to improve the robustness of physics discovery. This is the outline of my presentation today. Given a certain dynamical system, usually there are two problems to be solved. First, with sufficient knowledge about the system, we can characterize the system using a physics model represented by an ODE or PDE. Then the system behaviors and characteristics can be simulated by numerically solving the system. Unlike this forward problem, the second problem is an inverse problem. Given sufficient data measured or simulated from the system, can we accurately discover the underlying physics? Obviously, the inverse problem is more challenging than the forward problem, especially for a novel system that we have very limited knowledge about. So what are the benefits of attacking such a challenging problem? The knowledge discovery or equation discovery help us to establish an advanced understanding about the system. For example, what is the driving force of the system? What factors are trivial for the system? Additionally, with the discovered equations characterizing the system control as well as diagnosis and prognosis become more straightforward and efficient than the case without a physics model. So what is the state of art for PDE learning? Sparse regression is the most widely used type of methods in the literature for physics discovery. For a dynamical system with this general form, the objective of PDE learning is to construct the expression on the right-hand side given the measured data. Upon discretization, the time derivative can be expressed as a product of the library matrix theta and the coefficient vector C. Each column of the library theta corresponds to a specific candidate term for the governing equation. A key assumption is that the function on the right-hand side consists of only a few terms, making it a sparse functional form. As a result, there should be only a limited number of non-zero elements in the vector C. Therefore, this problem can be solved through linear regression with a regularization term that penalizes the model complexity. A fundamental limitation of existing sparse regression methods is that there's no ground truth for tuning the hyperparameter lambda. We have no idea about the correction model form behind the data. Therefore, how sparse is a big issue. PDE learning is different from traditional curve fitting problem. In curve fitting, a model is efficient as long as it has sufficient fitting accuracy and generalizes well to new data. In PDE learning, we are quite picky about the learned terms in the equation. For the example of the Berg's equation, the model becomes a lot more complex with the higher order term and more challenging to analyze and control, even though its coefficient is quite small. To solve the critical challenges in sparse regression methods of model discovery, in this study, we propose a new method to improve the robustness of PDE learning. It is called the Parsimony-Enhanced sparse regression method, or in short, the PeSBL method. This method starts from the noisy data. First, the data is denoised through neural network modeling by splitting the data into training and validation sets and setting early stopping. Then the denoised data is used to calculate the numerical derivatives and formulate the library matrix for sparse regression. Following that, the first Fourier transform is implemented to transform the problem from the temporal spatial domain to the frequency domain. In this process, the high frequency components are excluded because they are more susceptible to the noise disturbance. In this study, we developed a novel algorithm for sparse regression, that is the sequential PeSBL algorithm. This algorithm is developed based on the sparse Bayesian learning algorithm, that is the relevant spectrum machine. It prints the redundant terms sequentially. For model discovery, we introduced the modified Akaki information criteria to prevent selecting the complex terms, yielding the marginal increase of regression accuracy. Sparse regression uses a stochastic model for the investigated system because of uncertainties from memory to noise, signal processing, and model term similarities. The learned model usually has a large uncertainty. So in the last step of the PeSBL method, the Bayesian model updating is implemented by taking the outcome of sparse regression as priors and the manual data as the evidence. It can be expected that the uncertainty level can be significantly reduced after Bayesian model updating. Before presenting the results of PDE-learning using the developed PeSBL method, let's first examine its robustness by comparing with the existing methods in the literature. The Berkeley's equation is used as an example. First, we evaluate the effects of parsimony enhancement. It shows that using the PeSBL method with parsimony enhancement, the correct model form can be learned with accurate parameter values and low uncertainties. In comparison, existing methods in the literature without parsimony enhancement, such as the PeSBL and the S-cubed methods, cannot generate the correct model form. Additionally, we examine the effects of signal pre-processing. It shows that without pre-processing, both the PeSBL and SBL methods cannot generate the correct model form. After introducing signal pre-processing, the PeSBL method used the correct and accurate PDE model, and the SBL method used a much better model. Next, I will present the results of PDE-learning for several dynamical systems using the PeSBL method. The first investigated system is the dissipative system characterized by the Berkeley's equation. This is the system visualized in the spatial and the temporal domain, and a snapshot at t equals 0.3. For the case with the 20% noise, these are the model parameters distributions we obtained from sparse regression using the sequential PeSBL algorithm and the distributed distributions after Bayesian model updating. It shows that after Bayesian model updating, the accuracy and the confidence level are both significantly improved. These are the results of PDE-learning for this system with data containing different levels of noise. It showed that the correct model form can be discovered using the PeSBL method, even with the data containing as much as 30% noise. The second system investigated in this study is the traveling wave system, characterized by the KDV equation. Again, the correct model form can be identified with data containing as much as 50% noise. Another system investigated in this study is the system characterized by the 2D Berkeley's equation. It shows that we can correctly identify the model form with data containing as much as 50% noise. The last system we investigated is the laser-driven cavity flow, characterized by the 2D Navier-Stokes equation. Again, the results of PDE-learning is also very good. Here's a quick summary of this work as well as some future work we're working on. Thank you so much for your attention. This research is supported by NASA. All the materials can be found on this website.